Infinite Series, narrated by Dr. Rebecca Swanson, Colorado School of Mines. In this video, we are going to introduce geometric series and develop a method for determining their convergence or divergence. So a geometric series is a series of the form sum from k equals 0 to infinity a r to the k, where a and r are constants with a not equal to 0. The reason we call the series a geometric series is because the corresponding sequence terms are terms of a geometric sequence. Now let's recall from the previous section what happens to geometric sequences. The limit is either 0 if the absolute value of r is less than 1, it's a if r equals 1, and our sequence diverges for absolute value of r greater than 1 or r equal -1. Now let's say that S sub n denotes the corresponding sequence of partial sums. Let's write down a few of these. So S sub 1 is always a1, which in this case, the first term starting with 0 is just a. S sub 2 is a1 plus a2, which is a plus ar to the 1. S3 is a1 plus a2 plus a3, which is a plus ar plus ar squared. And so on. So this means that our partial sum formula is a plus ar squared, stopping all the way up at the ar to the n minus 1 term. Now, recall also that our series is just the limit of the sequence of partial sums. Now, the problem we have right now is that we don't have a closed formula. Those dots mean that as we take our limit, the number of terms is also increasing. So we have a problem. In order to actually take this limit, we need to find a closed formula. But lucky for us, a bit of algebraic manipulation can help find such an expression. So I'm going to begin by multiplying S sub n by r. That'll just increase the exponent on r for each term. And the way this helps us is if I take Sn and subtract off rsn, these terms cancel, these terms cancel, the term right after that plus sign will cancel with this one, and this term will cancel with the one right before this plus sign, leaving us with a minus a r to the n. Factor out an S sub n, and now we have a closed formula for S sub n that does not involve dots, assuming r is not 1. Otherwise, we would be dividing by 0. So we can go back now and actually figure out what's going on with this limit, with this series. We'll be taking the limit as n goes to infinity of a minus a r to the n over 1 minus r. The only term here that contains n is the a r to the n term in the numerator. So we can use our geometric sequence behavior to figure out what's going on now because we have a limit of a geometric sequence. So the first thing we'll notice is that as long as the absolute value of r is less than 1, this term goes to 0, giving us a over 1 minus r. In the case the absolute value of r is greater than 1 or equal to -1, we know it's going to diverge. So the only thing we have left to consider is the case where r equals 1. And this formula for S sub n does not apply because we assumed r was not equal to 1 in order to divide. But if we go back to our original series, if r equals 1, we just have a added up a bunch of times. A is not 0, so if we add up a infinitely many times, we're going to get something infinite or negative infinite, and so it's still going to diverge. So we can consolidate this and say the series diverges if the absolute value of r is greater than or equal to 1. And we now are provided with our first general series results in the case that our series is a geometric one. We'll end by applying this to an example. So here's our result. Okay. So we're going to determine whether this particular series converges or diverges, and if it converges, we'll find the sum. So what we'd start with is realizing that this is a geometric series. So we start out by saying that this series is a geometric series with A equal to 4, R equal to 1/5. Since the absolute value of R is less than 1, since 1/5 is less than 1, the series converges to A over 1 minus R, which is 4 over 4/5, which is 5. And that's the sum of the series, the limit of a series. The limit of the sequence of partial sums is a series, and that limit is what we call the sum. So as we end, just to summarize, you should be able to apply the geometric series formula to determine convergence or divergence of a geometric series. You will get to explore additional examples before and in class.